Good morning. I'm Professor Kiyoshi Hoshino from University of Tsukuba, Japan. This morning, I'd like to explain about eye tracking and measurement of eye rotation. First of all, I'd like to explain about our university. It takes about 7 or 8 hours from Japan to Singapore. Our university is located in Tsukuba. The city of Tsukuba is called Science City. That is because we have several universities and more than 100 national research institutes. It takes about 45 minutes by express train from Tokyo. Our university has a huge campus with about 15,000 students. We have Nobel Prize winners as well as Olympic medalists. That is because our university is started as a university of education. So we have a department of science, sports science. Now let's move to the first item of my presentation. That is rotational eye movement estimation based on the intensity gradients of blood vessels in the eye. This video clip shows how your rotational eye movement behaves. When your head is inclined right or left, your eyeballs rotate in the opposite direction. That is to avoid the accompanying inclination of your eyesight. The rotational movement serves as suitable physiological indicators for discomfort feeling and deterioration of physical conditions. For instance, car sickness, space sickness, visually induced motion sickness, visual fatigue caused by stereoscopic images, photosensitive epilepsy, their accompanying dizziness and sickness feeling are associated with rotational eye movement. Let me show you another example. The upper snapshot shows baseball hitting behavior, and the lower two are one is Japanese martial art, kendo, and another one is golf playing. In sports or martial arts, you're often led by a coach or leader to keep the core of the body straight and vertical. That is because once your head or core of the body may lean, the eyeball rotation occurs. That may reduce your sports performance. Let me show you one more example. Input from the vestibular system into the oculomotor system may induce irrational and involuntary eye movement. For instance, when you drive a car with higher acceleration, your eyes turn inward toward the nose, leading the narrower field of vision. And also, your eyes turn downward because the direction of gravitational acceleration turns diagonally backward. Some days ago, we finished designing a robot vehicle. It's always rolling, shaking, moving quickly, and stopping quickly. So once you come on board, your line of sight may change always with rotational eye movement. But the problem is the existing techniques for eye rotation always track the iris pattern for the measurement. But the pupil diameter varies depending on the ambient environment of lighting, followed by a change in the iris pattern. The iris gray patterns and their positions vary with the change in surrounding lighting environment. That means the system always need light shielding. As the solution, we focus on the blood vessel image of the eye because it has high contrast, it's robust to eyelids, blinking, eye movement. It's also robust to pupil diameter change. The point here is in the conventional method for rotational eye movement estimation proposed by our group, an area that includes a blood vessel near the iris in the white part of the eye is used as a template image for tracking, and the selected vessel is usually thin and pale in the image. Without blue auxiliary light for contrast enhancement, a large estimation error may occur. In this presentation, we propose a method that allows rotational eye movement estimation with high accuracy without using a blue auxiliary light for users, between whom blood vessels in the white part of the eye differ considerably in terms of thickness and density on the image. In the proposed system, in order to select a template image that includes a thick, dense blood vessel suitable for tracking in the white part of the eye, feature points are first extracted from the white part of the eye on the acquired image based on the intensity gradients. And the number of feature points in a candidate template image is counted. Second, from among the candidate template images that include a large number of feature points, those with a reflection of external light source are excluded. Third, a candidate template image that includes a blood vessel with a distinct shape, that is to say, no blood vessels with a similar shape exist nearby, is selected as a template image. First of all, in order to obtain a region suitable for tracking, that means a robust area against a certain amount of illumination changes, feature point detection using oriented fast and ro ro rotated brief, hereafter referred to as ORB, one of the methods for local feature detection, was performed. The fast detector in ORB detects multiple feature points as adjacent pixels. Therefore, the information, the thickness of a blood vessel, can be obtained as the number of feature points detected. In addition, it's possible in ORB to set the threshold for feature point detection. This allows detection of only points with strong features, those considered to reflect high density on a blood vessel on the image. As, as a preliminary experiment, we performed feature detection using ORB and other local feature detection methods. in the white part of the eye of several subjects. The results showed that compared to the other feature detection methods, ORB detects more feature points along the blood vessels that provide a good amount of contrast against the white part of the eye and less feature points in the white part of the eye. So it's possible to select a template image that includes a thick, dense blood vessel based on the number of feature points detected using ORB. Each of the candidate template images has the information on the number of feature points included in the image, and the information was used to rank the candidates in descending order of the number of feature points. The higher the rank is, the robuster is the area against elimination changes. The candidates were narrowed down, starting from those in higher ranks. Candidate template images were ranked by the number of feature points included in each image. However, when the light from the relatively powerful light source located nearby is reflected on the eye surface, more feature points were extracted based on the intensity gradients caused by refractions. And the regions with refractions were ranked higher in the candidate ranking. Therefore, processing was performed to remove template images with refractions from the candidates. First, an illuminance histogram of the white part of the eye was created, and the brightness values in the top 10% of the cumulative frequency was determined. If a candidate template image includes more than 25 pixels, that is 1% of the number of pixels in the white in the image, whose brightness value were within the range determined, the image was judged to include refractions of ambient light and was skipped. Let me show you how our system works by some video clips. In this video, the system is tracking the blood vessel with stair-like shape. In the experiment, each subject wearing the measuring device tilted his head to the right and left by 60 degrees so that rotational eye movement is induced by vestibulo-ocular reflex. The eye rotation angle observed in a person with dizziness or visually induced motion sickness is about plus minus 8 degrees. In order to evaluate whether the occurrence of these symptoms can be well estimated, the motion here was performed so that the eye rotation angle becomes about plus minus 10 degrees. Dynamic images were acquired during the motion, and the angle of the eye in the initial frame was determined as a reference angle. That means eye rotation angle of 0 degree. The eye rotation angle in each of the following frames was determined by calculating the difference from the reference angle. You can see in this figure that the estimated eye rotation without system matched well with the observed data. In the experimental results here, is in multiple subjects using whose vascular morphology in the white part of the eye differs considerably. Measurement was performed in the following three different lighting environments: with a strong blue light, with a weak blue light, and without a blue light. With a strong blue light, highly accurate estimation is possible with both the conventional and proposed methods at a similar level of estimation accuracy. However, the amount of estimation error with the conventional method increases as the intensity of the blue light decreases. On the other hand, highly accurate estimation is possible with the proposed method, regardless of the lighting condition. These results suggest that the rotational eye movement estimation that is less affected by lighting conditions in the surrounding environment and the individual differences in vascular morphology can be performed with high accuracy by using the intensity of gradients in the white part of the eye. Now, let's move to the second item: eye gaze tracking that doesn't decrease the estimation accuracy when an eye is captured from the side. Let me explain about features of conventional and proposed systems. In the conventional system, gaze estimation is performed with the camera placed at the front within the effective range of about plus minus 15 degrees horizontally and plus minus 10 degrees vertically. Through the calibration performed by solving the common quadratic equation with the least squares method, using a total of 9 fixation points in a grid form. The proposed system, even if the camera is placed on the side of a face, effective gaze estimation range of around 40 degrees. By using the proposed optimum 6 fixation points, it doesn't need necessarily form a grid. I'm going to give you a good solution. A wide effective estimation range can be obtained by maintaining the estimation accuracy equivalent to that of the conventional system, even if the camera is placed on the side or in any direction, by selecting 6 fixation points for calibration by forming a pentagon of a wide area in almost equal side length. The movements of the center of the pupil that are captured are left-right reversed against the line of sight. But it must be noticed that the distribution of the coordinates of the center of the pupil distorts non-linearly if any eyeball is captured from the horizontal direction. For instance, if a grid pasted on a sphere is viewed from the diagonally downward position, the grid appears to be non-linearly deformed, as shown below. I'll give you one example. An eyeball of a right eye is captured by a camera at an angle of 60 degrees horizontally and 40 degrees downward vertically. The triangle with red color is the area at the center of the pupil when the user gazed in the downward direction on the same side of the camera. This one shows the area at the center of the pupil when the user gazed in the upward direction on the same side of the camera. This triangle with red color shows the area at the center of the pupil when the user gazed in the downward direction on the opposite side of the camera. And finally, this one shows the area at the center of the pupil when the user gazed in the upward direction on the opposite side of the camera. Let me show you how to select 6 fixation points. A fixation point is always presented one by one in order from a corner. If the pupil center is captured or the system detects the center, each process completes. Then, at the second step, a fixation point is also presented one by one in order from the corner. Circled numbers with underline are the fixation points where the center of the pupil usually can be detected. Here at the third step, the height of step 3-1 is the middle of steps 1 and 2 that have been determined. If the number can't be divided by 10, that means if the camera is positioned slightly below the user, the fraction is raised to the nearest whole number. It can be truncated also. At the fourth step, the height of step 4-1, theta y is lower than step 1 by minus 10 degrees that has been determined. However, minus 30 degrees is the minimum. Theta x is the middle point of steps 1 and 3 that has been determined. If theta x can't be divided by 10, truncate the fractions. That means select the number closer to 0 degrees. However, the number can be raised to the nearest whole number also. The height of step 5, 1 is theta y is 30 degrees and theta x is a middle point of steps 2 and 3 that has been determined. If theta x can't be divided by 10, truncate the fractions. That means select the number closer to 0 degrees. However, the number can be raised to the nearest whole number also. The sequence of steps 4 and 5 can be reversed. Now we come to the final step. Find the centroid of the pentagon that is created by step 1, 2, 3, 4, and 5 and define it as 6, 1. If the centroid is not positioned at the nodal point in 10 degrees unit, select the nearest nodal point. The pentagon indicated by dotted lines here is just an example. We have designed some prototype measurement system like this with small cameras fixed roughly next to the eye for the experiments and the system evaluation. Now, let me show you some examples of estimation results. Here, gaze estimation is performed by placing the camera at the front of the face and performing calibration using 9 fixation points. That is same as the conventional system, within the range of visual angle plus minus 10 degrees. You can see that the estimation accuracy is quite good, but the dynamic range of estimation with high accuracy is narrow. Here, gaze estimation is performed by placing the camera at an angle of 60 degrees horizontally and performing calibration using 9 fixation points in a grid form within the range of visual angle plus minus 10 degrees in the same way as the conventional method. You can see that the estimation errors are so big on the area and direction of the opposite side of the camera. Here, gaze estimation is performed by placing the camera at an angle of 60 degrees horizontally and performing calibration using 9 fixation points in a grid form of a wide view angle range plus minus 20 degrees. You can see the estimation accuracy is not so bad. However, it happened to be a satisfactory result by chance. The visual angle range where the pupil center can be detected varies depending on the individual. Because if capturing of the pupil center from the 9 fixation points that are presented in the grid form is to be ensured, the gaze estimation effective visual field becomes narrow. Finally, gaze estimation is performed by placing the camera at an angle of 60 degrees horizontally and performing calibration using 6 fixation points By applying the proposed fixation point system, gaze estimation is performed by placing the camera at an angle of 60 degrees horizontally and performing calibration using 6 fixation points by applying the proposed system for a different user. You can see, through proper selection and presentation of fixing points for calibration, almost equivalent estimation accuracy can be obtained, as that obtained by performing calibration using 9 fixation points, even if the camera is not placed at the front, especially it's placed at an angle of 60 degrees horizontally. Even when the visual target is moving, not fixation points, but visual targets for a user to gaze, our system can estimate his line of sight with high accuracy. Now we come to the conclusion. Please imagine when a camera for capturing the eyeball is placed almost directly to the side so that it doesn't obstruct the user's field of view, estimating the line of sight with this method. Because the eyeball is a sphere, the pupil center coordinate is distorted, and this caused the issue of low eye tracking accuracy. The speaker introduced a new eye tracking method that doesn't reduce the accuracy of estimates, even when the pupil camera is almost at the side of the eyeball, and that requires only a little calibration. In this method, the user is asked to look at the minimum of 6 points of light that include the corners of a pentagon that is slanted toward the inside corner of the eye and the center of gravity of that pentagon. This is a calibration method that maps line of sight angles from the pupil center coordinate. The speaker also introduced a method to measure rotational eye movement by using a small camera installed almost by the side of the eye in the same manner as the eye tracking. This method uses the characteristic images of the blood vessels in the white part of the eyeball. A template image is selected based on 3 criteria. First, the blood vessel must be thick and have good dark light contrast. Second, there mustn't be any external light sources refracted. And third, there mustn't be blood vessels with a similar shape nearby. By continuously tracking the area where the degree of similarity in template matching is maximized, there's little interference from the refractions of external light sources, so that highly accurate measurement of eye rotation is possible. A part of this work was supported by the Ministry of Education, Culture, Sports, Science, and Technology, Highway Research Foundation of Japan, and Suzuki Foundation. A part of this work was also commissioned by the Ministry of Internal Affairs and Communications and the scope. The speaker and our research group are grateful for those supports. If you have any questions or you are interested in our researches, please email to me. Thank you.